And welcome back. We have just one last topic to get into with this bit on the triangles. After this, we will get into even more general trigonometry, not about circles, not about triangles, just about sines and cosines. And the reason why we're going to be able to do that is through what we're about to say now. You see, we've done radian measure, we've done degree measure to describe the same thing. They both described angles. We did the unit circle approach, we did the right triangle approach, all to say the same thing, which was general trigonometry. Right, we had sine defined through the unit circle, we had sine defined through right triangles, we had cosine defined through each, tangent, we did inverse trigonometry through each, we did all of trigonometry, all of the essentials and fundamentals of trigonometry we did through both avenues. And also, most recently, maybe more concrete, we just did the law of sines and the law of cosines. And those are also sisters. They don't, well, maybe brothers. They're siblings. They don't quite do the exact same thing, right? They handle different situations in turn, but they are going about doing the same goal, which is solving for dimensions of triangles. And so whenever you have the option to do one or the other, right, if you had a case where you could use either the law of sines or the law of cosines, the question often arises, which am I supposed to use? And actually the questions has arisen for these other issues too, right? What measure should I give my angles in? Should I use degrees? Should I use radians? People have asked me, should I use the unit circle definition of this or that? Or should I use the right triangle definition of it? Should I use my ratios, or should I use the nice values on the unit circle? And, well, to all those questions, the answer is always going to be use what works. And in the event that everything works, use what works best for you. Some of you are more comfortable working in degrees. Some of you are more comfortable working in radians. There are times where you have to do one or the other, but when you have the choice, choose what works best. Let me bring something to light here. It is going to be often the case that we're going to work with something that's interchangeable, right? Radian measure and degree measure are obviously interchangeable. We've taken great pains to show that unit circle approach and right triangle approach are interchangeable in that they produce the same results. Trigonometry is universal, right? There's not some weird exception if you did it one way as compared to the other. For instance, here I have an example, right? If I rotate by some angle theta, and our terminal point wherever we end up is on the line y equal x, then it's going to be the case that tangent of theta is 1. And this is for standard rotation, or movement on the unit circle, or any other such thing. And it could be that the theta was in degrees, or it could be that theta was in radians. It doesn't matter. However you justify it, tangent of theta is 1. And you can do it any number of reasons, right? If you're on the line y equal x, then tangent of theta, using the unit circle approach being y equal x, is just 1. Or you could have recognized, oh, y equal x, that puts me on a 45 degree, 90 right triangle. And so the reference angle is 45 degrees. I'm either in the first or the third quadrant. Tangent's always positive, so tangent has to be 1. Any of those reasons justifies what we set up here. Tangent of theta is 1. However you choose to justify it, using obviously the right reasons, right? You can't just justify something willy-nilly. You have to use something that works. But in the instance that there's more than one thing that works, pick the one that works best for you. So should I use law of sines, law of cosines? Use the one that works best for you. Assuming, you have the option. And that brings us in now to application problems. We do what works. And so permit me, if you will, to introduce a terrible song reference. It's a blue man. He hops into his blue Corvette and then he starts driving. He drives for 100 miles with a heading of 60 degrees south of west. From there, he drives 250 miles straight northwest. So how far after he's hit the end of that does he have to drive, and in what direction should he drive to get back to his blue house with the big blue windows? This is something we can answer using what we have. We have to do what works, but we can do anything that works. Let me illustrate here what this trip looks like. Here's home, the big blue house. I should have used a blue label for that there, sorry. But there's this big blue house over there with the orange font. And he first drives 60 degrees south of west. So if west is out this way and south is this way, well, if you're going west and instead you go 60 degrees south of that, you are going in this direction. And after having traveled 100 miles, you're done. Then you turn northwest and you go 250 miles. And this is straight northwest, so the angle of elevation here is 45 degrees. And then the question is, from there, how do I get home? How far away am I from home? And in what direction do I need to drive in order to get home? If you are comfortable or familiar with physics, mechanics, this is a vector problem. Right? What is the distance and direction? What is the magnitude and direction of my vector? So this is incredibly relevant to some of your very specific interests coming down the pipe. Well, the way you can answer that is, hey, we got a triangle. Right? I've got one leg, another leg, and, well, not quite a hypotenuse, just a third leg here. I've got three sides of a triangle. I know the length of this red segment here, it's 100 miles. I know the length of the blue segment here, that's 250 miles. And also, given the directions of the first two legs, I can actually deduce this angle included between those two sides. Right? Because if I'm going 60 degrees south of west, that actually puts, if this dotted line were to be true vertical, that would make this angle right here 30 degrees. And also, in being true northwest, that makes each of these guys 45 degrees. So this included angle is 30, 40, it's 75 degrees. So we have two known sides and a known included angle. So to find this missing side, we could very well use the law of sines. Just kidding. The law of cosines. That one. Right, we have two known sides, a known included angle. That's the calling with which the law of cosines can answer. And we find it to be about 244 miles. And then to find the heading, the direction we have to travel to get home. Right, it's not just point home and drive this distance. That's not good enough. I need to know the direction I'm traveling. And we can again use the law of cosines to find that missing angle. Well, kind of. Right, using the law of cosines, we find this angle right here. Which, I mean, is technically viable. That tells me, okay, wherever I'm going, reverse direction and angle myself northward by 20, however much degrees it was, 23.3 degrees. Angle yourself upward and drive, you'll find home. That's definitely true, right? That's definitely true. But the more conventional way would be to give your heading, to give your direction, relative to the four cardinal directions. Like drive east makes a lot more sense than angle up by 30 degrees and then drive. So to give us a heading based on north, south, east, or west, it would actually be more useful to find this angle right here. And since the whole thing adds up to be 45, we can take the 23 we found out of 45, and we'll get our final heading. If we drive 21.6 degrees south of east for 244 miles, we'll be home. That's what works. But it's not the only thing that works. And actually, There's a reason why in physics classes you don't get exposed to the law of cosines. The law of cosines is pretty much good for triangles. Let's suppose I had a additional thing I did. My blue man, blue Corvette, big blue house, big blue windows, everything's blue to him and himself because he ain't got nobody to listen to. He hops in his car, he drives. Same as before, 100 miles, 60 degrees southwest, 250 miles northwest. But then, instead of driving home, he proceeds to drive 50 miles straight north. So how does he get home now? And suddenly the issue gets much more complicated. Because yeah, I've got this again. I have a triangle there, but I'm not going home from point B. I'm going home from point D. And uh-oh, I ain't got no triangle. I've got a quadrilateral, and the law of cosines does not apply to quadrilaterals. I'm kind of stuck here. But we do what works. And there's two things that works. One thing is you could first solve for triangle AB home. Right, we can find this side here. And suddenly I have now two known sides for triangle BD home. I've got this old return trip leg, and I've got this new leg 50 miles north. I could then use that to find my final true heading from point D. That's awful. I would have to use the law of cosines upwards of 4 times. To tell you the truth, the way that this is handled in physics classes and more generally in engineering applications is to say, you know what? I'm just going to break each of these legs down into right triangles. So for this first leg, I'm going to find how far down I went and how far to the left I went. For the next leg, I'm going to find how far to the left I went and how far up I went. And then, of course, for this last leg, it's just how far up I went, 50 miles. And I'm going to add all the left, and that's my overall left. I'm going to take my down, subtract that out of my 2 ups, and that's my total up. And I'm going to end up with what will amount to this right triangle right here. And that's just by taking each of these components and adding them all together, producing one nice right triangle. So to answer the questions about to be asked, do I need to remember law of cosines in real life? Not really. But at the same time, can you take the equation that is given to you, and can you use it to solve for unknown bits? Because, well, that's the same thing that you will be doing in further applications with the vector components as illustrated here. So you might as well see if you can do it a little less generally first. So can you do what works? And that brings us to the end of this. I'm not going to get into calculating that return trip. If you want to do it, by all means. If you want to do it with 4 iterations of the law of cosines, if you want to do vector analysis, do what works. That's the name of this game. And so this has mostly been just an excuse for us to slow down a little bit before the break, get everything nice and wrapped up with triangles, and then following the break, we will start getting into analytic trig. So let me know how you feel about all this stuff, and I will see you up ahead.